Going today. There are a couple of things about the current assignment. Yesterday, some of you came over for the office hours, and so I wanted to clarify a couple of things in this question 10.25 from the book. This is about the neodymium doped YAG Q switching in a YAG laser, and so there was some confusion about the states. This is a figure from your book, chapter 10. Details not terribly important, except that you are essentially pumping from the ground state manifold into this state out here, and there are two states in there, very closely spaced in energy. So you're using a broadband light source perhaps, and then you're going to causing transitions into both the states, not just one. And I think yesterday when we were discussing, and there was a question of how do you find what do you mean by the initial concentration or initial population of carriers, which is asked here, initial density of atoms in this manifold, and then the final density of atoms in the manifold. Okay? So I said during the discussion yesterday that was before you even start pumping, meaning when you are here, but that's not correct actually. What I wanted to say now is the initial is really about the Q switched initial, meaning when you have pumped it, say 3 times the inversion threshold here, for example, or 5 times, or whichever, much higher than the inversion threshold. That density is what we are calling initial, and the final density here in this question is once you Q switch, you extract all the energy, and it stabilizes to a low value NF here, and final. That's the final density that's being asked about here in this question. So it's this and this. So just as a very quick thing, so there's a discussion there about the Boltzmann distribution, and the Boltzmann distribution is within this manifold itself. If there are 2 levels and you know the density in, so here are the 2 levels, and here's your ground state, and you have pumped both of them basically, and you have some in this state, lower level, and some in the upper level. So within this manifold, they are Boltzmann distributed, meaning n upper by n lower is equal to e to the power minus e upper minus e lower over kt, and you're given all these quantities, you're given kt, these energies as well. So basically what we're saying really is find out what is the n upper and n lower, such that the n total in this excited state, which is n upper plus n lower, is the initial. I mean, that's basically your threshold. So if you know your gain threshold, which you can find out from all the other parameters like losses and gain per unit length, mirror reflectivities, etc., cross section, you can find n threshold, then find, if you have pumped it 3 times or 5 times, find what is total n initial. From there you can find individually how much each one of these is. So that's what we meant. And during the discussion, I initially thought they're asking what is the population here. You can also find that, but that's not what's being asked here. So that was clear to me. And n initial and n final for any Q switch laser are related through this expression, which is also derived in a book and derived by Professor Pollock in the class, so that you can use. And there is also a little chart in your book. This is a transcendental equation, not analytically solvable, so you can either ask Mathematica to do it or look up this little chart which plots it and say that if you are 5 times threshold or 4 times threshold, use this value of ni by n threshold, and so you can use it to get what is being asked there. Now there's one more question about part C of this question. Now what I would suggest at this point, and I'll send out an email, is you can skip it. It's actually, all it's saying is do not, assume what would the problem look like if n1, which is the lower level here, was 0. If you think you have solved it, that's great. If not, you can skip it. It's okay, because it's all right. So that would be a bonus part. If you just do it, that's great too. Okay. Yeah. And the second question I wanted to address was the question number 1 in the assignment, where there was quite a bit of discussion yesterday or confusion about what is an etalon, And I want to just clarify that part. So, so if I have a gain medium in a laser and it has its own FSR and all that sort of thing, let's actually sketch this out. And so here's my gain spectrum, small signal gain spectrum, and it has a certain FSR based on the cavity size, etc. And now, if I have inhomogeneously broadened gain, it's typically a large broadening, and let's call this as delta nu for a second. It's the broadening of the gain spectrum. And the echelon here would be a thin plate of glass or high reflectivity glass or something like that with a certain thickness T. And that essentially is kind of an additional cavity with two reflectivities on both sides, assuming it to be the same on both sides, the air-glass interface reflectivity. And based on that, you'll have a certain transmission coefficient through that echelon as well. So you'll have a certain transmission coefficient. But the whole purpose of introducing this is to, if your cavity size was this much first initially and your FSR was closely spaced, meaning you had multiple modes, but if you introduce a much smaller, this is another cavity, and you can have a FSR that is much widely spaced now, and you can push out the allowed modes out into parts of the spectrum where you are below the gain threshold, and then you have loss. So you can do that, and that's the purpose of this problem, meaning trying to design the reflectivity, choose the reflectivity of this little plate such that I'm able to push out the FSRs out here such that they go below the they're in a loss spectrum now, not in the gain spectrum. So that's the purpose of this question. And I think also during the discussion there was so there was also the question of what is the gain the bandwidth given here? What is that line width that's given here, right? And I had mentioned that, I mean, the problem, the way you kind of want to solve it is without the FSR, without the echelon, what happens here, but with the echelon, your path length changes a little bit, and the FSR changes, and whereas what doesn't change is the reflectivity of this mirror and the reflectivity of that mirror. That doesn't change. I mean, this mirror, this echelon does nothing to those. So the total internal loss inside the system still remains the same. And what I had, I think there were a couple of questions of what is this bandwidth that's given, or the line width is given? Is it this line width, or is it the line width of the whole homogeneously broadened spectrum? Right? That was the question that was asked as well. And I want to clarify it. I think yesterday I probably told you that this was the line width. I did tell you that this was the line width of the allowed cavity modes. But as you know, that would be determined completely once you define the losses. Then you completely define what is the line width of it, right? Losses R1 and R2. If you have any additional losses here, they all completely define this line width from your cavity problem. So, if you also look at that number, it is way too large to, that the number that's given is way too large for a cavity line width. So, essentially, if you took notes of that, change that to the line width of the gain spectrum. That's what's given here. This 37 gigahertz or whatever that's given. That's the line width of the gain spectrum, the entire gain spectrum, inhomogeneously broadened gain spectrum. So if you assume a Gaussian for this thing, so that's what's given here for you. Is that clear? And just want to clarify this because there was a long discussion yesterday about that. And the line width of the individual modes allowed by the FSR of the cavity, that is completely determined by losses in the cavity itself. Okay, so the less is the loss, the sharper is the line width is smaller, and the sharper is it, and higher is the Q, etc., etc. So those two clarifications of the current assignment, and it's due this Friday. So not today, of course. I think I've sent out an email about that. And if you have any further questions or want to discuss more, we do have an office hour. I have office hours 5 to 7 p.m. today in my Philips office. Yeah. Okay. Okay, so I want to get back to continue our discussion on semiconductor lasers, and we had very qualitatively outlined some traits, kind of nice things about a semiconductor laser. The fact that you can have kind of inject, apply voltages that are, relatively small related to the band gap or the energy gap of a semiconductor. The voltage you apply here is very close to the energy of the photon that's going to come out. So energy of the photon, let's say it is 2 electron volts, then typically you'll be applying about 2 volts on this. If the energy of the photon is 3 electron volts, you'll be applying 3 volts, or slightly more, or close, something very close. So and I think you quantum mechanically also understand what is 2 volts. It's you are giving. That's the extra energy you're giving to electrons, and and basically you're injecting carriers which have an excess energy of 2 volts or 2 eV, and large part of it is converted into photons here. So a large part of it essentially comes out photons. On the other hand, if you're looking at larger gas lasers or solid state lasers, you're typically talking about kilovolts or hundreds of volts, because you want to inject electrons and make them collide with things, and if you look at excimer or whatever, so you're applying very high voltages there. Here you're applying very small volts and injecting reasonable amounts of current, which is why it makes it easy to make handheld lasers and mobile and as well. And the efficiency of this is also extremely high, and you can get very high power output. There are obviously disadvantages as well, and we will discuss them when we talk a little bit more about mode profiles, etc. For example, the mode profile here, it really spreads much more. When the laser beam comes out, you have a couple of degrees or more of beam spreading when the light comes out. But I think we know that laser light is coherent, so you can always put a lens and you can collimate it back. So that's the beauty of it. If it was an incoherent light source like a LED, if you put a lens, you're never going to be able to kind of collimate it back again completely. You always have some diffraction and additional diffraction, but so you can collimate it back. But then there are some other issues. For example, the coherence length and coherence times are not as good, or the line width are not as good as, say, an atomic system-based laser like a neodymium. I mean, like let's say gas laser or something like that. But many of them are. So it's on the other hand, the advantages here really outweigh in some sense the disadvantages, because it's obviously very efficient. You can modulate it directly. You can turn it on and off directly. You can modulate the signal directly by just applying an AC voltage. So remember, if you're applying kilovolts, you cannot modulate it at a gigahertz frequency. It's very hard to. If you have very high volt, you cannot modulate it fast enough. But here it's very easy. In fact, not just easy. It is actually regularly used for optical communications and such, right? So let's get into a little bit of the details. I'll first start by making a connection. So hopefully by the end of the class today, we'll make this connection, that what is the gain spectrum of a semiconductor laser. And we'll see it's actually very similar to what we have done for atomic lasers. For atomic lasers, we have found that the small signal gain spectrum is your Einstein A coefficient, or the spontaneous emission rate, or 1 over the lifetime, times the wavelength of emission square over 8 pi times refractive index squared, times. So what I'm writing here so what you have for an atomic system is you have the line shape, and I'll just briefly recap that one more time. And then you have population inversion. If you have G2s and G1s, you can put them in here. So that's your gain spectrum, out of which we used to write this as our cross section with area, with units of area per centimeter square, and this is our in centimeters square, and the orders of magnitude were 10 to the minus 12 to 10 to the minus 20 for atomic systems. And this is our density of atoms per unit volume in 1 over centimeter cube, typically 10 to the power 15, 10 to the power 17 or something like that. And the product of that gives you the gain coefficient in inverse centimeters, right? So, and typically, you know, one is kind of a high typically for a gas laser, I would say, 1 inverse centimeter or something like that. And then the losses would be much smaller than the gain if you were to laser at all. So, and what is the physical meaning of this again? So if I take this media that has this gain spectrum, small signal gain spectrum, and I'm injecting photons into this gain medium, and this is the gain whether or not you make a laser with it. You know, laser happens to have a cavity around the gain medium, but even if you don't make a laser out of it, you can always create, so you can pump it and create population inversion, and then you'll have, if I have a certain intensity of light in, the light out may be larger or smaller depending upon the value of this. You know, if it's positive, if gamma is positive, then I out over I in, let me write that down, just as a recap of what do we mean by gain here. So as the photons go in, I have maybe 5 here, or you know, and then 10 here, and then maybe 30 here, but it increases exponentially as long as you're in the linear regime. The number of photons increases exponentially as you go across, and that we so this is the rate the differential equation that tracks what is the change in the intensity of photons as you go in Z. So that's how we had a very quick recap of the basic concepts of any laser for that matter. So and that's what led to, if I have length L, I have intensity at 0 times e to the power the gain spectrum, or the gain coefficient times L, right? So that's the increase. I out over I in is exponential of the gain times the length, the gain coefficient times the length. Now if that's the small signal gain, and so classically, you know, quantum mechanically, you can count the number of photons. Classically, what's going on is you have your electromagnetic wave whose amplitude is kind of increasing, so you're optically amplifying. It's an optical amplifier, amplifying the number of photons here, right? So, and where is that energy for that amplification coming from? It's coming from the pump, which is a DC pump here. You're kind of taking that energy, converting into a more directed single frequency energy, right? So and the other details which I don't want to get into right now is if you have, if your intensity, as you know, no exponential is forever in some sense, right? So if you reach very high intensity and at some point you can gain, the gain will saturate, because every time you create inversion, you are losing this and you're gaining this, right? So the gain spectrum collapses slowly. So that is taken into account by the large signal model, which adds this little thing here. You're solving a couple of assignment problems where you have to deal with this aspect, that there's, you know, a large signal gain, which when your intensity gets too large, then you have to consider this, that the gain coefficient effectively is dependent on intensity, so it goes down. If the intensity is very low, then this is 0. You forget this and you're exponentially increasing, so you're in small signal. And large signal is when you clamp that down, so it doesn't increase as much. Okay, so what we are going to do for the semiconductor laser today is exactly the same thing. We'll identify and we'll first find that the gain spectrum, how does it change? How does it look for the semiconductor laser? And we'll use the same ideas, and instead of a solid state gain medium with atomic populations like this and a line shape like this, we're going to replace it with a semiconductor now. And so if I were to take a semiconductor and go to population, invert it, what's the gain? And we'll see the expression for that will be similar, but that's what is going to drive some of the new concepts we're going to introduce today. So what we'll get again here is, you know, the wavelength dependence will be very similar, 8 pi n square, but now n was the refractive index of this media. If it is mostly air, it would be 1, but inside a semiconductor, it's never 1. Right? Inside a semiconductor, you have a dense set of atoms. Refractive index typically 3-ish, depends on which semiconductor you're looking at, maybe 4 for narrow bandgap semiconductor. narrower the gap, the larger the refractive index, etc. So we'll discuss those later. So instead of the line shape, we have something which is the heart of the problem, and I'll spend some time describing it today. It is called the optical joint density of states. Let me write that down first here, just the notation. Okay. J and T, joint density of states. Rho is the density, so this is the optical, and it is extremely characteristic of the photon energy and the semiconductor you choose. It will have all the information of the semiconductor as well as the photon energy in it, and I'll describe it today. Optical joint density of states. J dot, so what it's sometimes referred to like that. And so the line shape gets replaced by this optical joint density of states. And the population inversion, instead of atomic the number of atoms in any level, gets replaced by Fermi functions here, because we are going to look at how once you release electrons in a crystal, they can obviously spread out. Electrons are waves, so they will form their spread out states. And now if you want to find out how many electrons are there in a once you put electrons in a crystal, we'll see that you'll form manifolds of energy again in some sense, right? You form bands, and there'll be a gap between them. And the occupation function of the number of electrons will be given by Fermi-Dirac distributions, and we're going to talk about that. Let's say this is the conduction band, this is the valence band. We're going to talk about them today. And each one of them will have a separate Fermi function. We're going to ideally every system, once you're in equilibrium, all the electron populations, whether you're in this manifold or that manifold, have the same Fermi level. But that's useless to me as a device, because in equilibrium nothing is going to emit light for me. So I'm going to have to force it to emit light. So I'm going to pull it way out of equilibrium, and I'm going to invert it. I'm going to put a lot more electrons here, and I'm going to empty out a lot of states here. So that will be electrons, that would be holes. And this measure of how far out of equilibrium have you pushed the system of the semiconductor system is given by this difference function of difference of the Fermi functions. So you will see that this will be Fermi function of the conduction band at some energy level here, let's say E2. These are general values. And some energy level E1, such that E2 minus E1 is equal to the photon energy. There will be a recombination between these two states, and the photon will be emitted. And we'll see now that so the population inversion in a semiconductor takes the shape of a distribution of electrons, as you would imagine, because you have a bunch of electrons. It's a band, not a single atomic state anymore. The orbitals are not localized. Quantum mechanics says that if your electron is in a bound not in a Coulomb potential of an atom, but a whole crystal, which could be centimeters wide, then its energies, or it can have many wavelengths which fit in the crystal. It spreads out, so one needs to now take into account the Fermi functions of these distributions. So this is our new population inversion term corresponding to N2 minus N1. So, but physically you can intuitively connect to it. FC means occupation probability of the conduction band states. That's kind of N2, right? And FV means occupation probability of the valence band states. That's like N1. It's similar, N2 minus N1, very similar. And that's the connection here. And there is let me just start by saying that we will end up here, but I will have to. The first statement is this is a triumph of last half a century of quantum mechanics and solid state physics. There is a wealth of information buried inside here, that electrons form bands in solids, they form block states, they and there'll be basically H bar floating around in every equation, and you know that it's completely quantum mechanical as a result, right? And there is also a lot of concepts of equilibrium and non-equilibrium buried inside here. And so there's thermodynamics buried in here, there's a lot of quantum buried in here. And not only quantum of electrons, it's the quantum of light-matter interaction. What we'll see now is this optical joint density of states. Let me write this down. We'll derive this today. So it has a classic sort of, or rather, this is how it's going to look. The optical joint density of states as a function of frequency of light. So there's the frequency of light, or the energy of light sitting here. It's inside a square root for 3D semiconductors. There's the band gap of the semiconductor. This is completely a quantum mechanical effect. Basically, electron interference and standing wave formation in crystals leads to band gaps in semiconductors. There is a reduced mass. So this is a reduced effective mass, meaning if electrons, we'll see that the reduced mass is going to have the information of electrons in the conduction band and electrons in the valence band. I'm going to, kind of explain these things today. Anyway, every time I look at this expression, I really think it's a very interesting, very beautiful equation. It has so much of some of the biggest findings in the last century of quantum mechanics and thermodynamics is buried inside this. And it will explain to us pretty much, so this is the gain spectrum, and this we'll use it to explain an LED, a solar cell, any optical device you want, whether it's absorbing, whether it's emitting, a photodetector, a laser, all of them will be explained with this. So that's why it's a very sort of overarching sort of result. And we'll see, but hopefully now we can make a quick connection to the atomic system. And once we do that, we are at a, starting not from scratch, but we're already starting at a very high level already. So I just want to make that connection first. Okay, so let's start looking at what happens. So where does this come from? And before I get into all the details, let me just say that this is not the course to get into solid state physics and to explain all the minutiae of how bands form and what is the effective mass of bands and all that. For that we have, for example, in our department we have 4070, which is, for example, taught next semester. That's solid state physics of semiconductors, of nanostructures, quantum wells, wires, dots, all that sort of thing. But if you understand one structure, 3D, dots, wires, nanostructures is absolutely a trivial extension of this. A very simple trivial extension of all these things, the low dimensional structures. The main conceptual advance is understanding the 3D part first, and then all these others are small little tweaks on top of that. So let's look at the 3D part first. And actually, before I go there, I want to also give you a bigger picture of where will this lead to. So this is going to be the gain spectrum, this whole thing. And when you make a plot of it as a function of frequency, you see this goes as a square root of frequency minus a certain gap. And you're going to plot it. So when the system would be sitting under equilibrium, there will be no electrons in the top band. They will all be in the bottom band. So Fc would be kind of close to 0 or very low. Fv would be very high, close to 1. So you get a 0 minus 1. So you get a negative number at equilibrium. Right? Just like in an atomic system, all the ones that want to sit in the bottom, not on the top. So instead of gain, you get loss. Just like that. Same thing. Here you get loss, and you can get loss because of that. So if you want to plot it, it will go as square root of energy minus h nu minus Eg. It will start at the gap, and you will have loss. And then you connect your battery to the semiconductor laser diode, and what you do is start, when we apply our voltage across the battery, we are tweaking these two directly. Every volt of battery voltage we apply, we are moving one of the Fermi functions one eV above the other. So that's what you're doing. So you go from like -1 all the way to +1. You tweak it completely such that you get population inversion. You get like this will get close to 1, and we'll see this we can make it close to 0. And when you do that, you invert the spectrum. Instead of loss, you just mirror reflect it over here, and you get gain now. And we'll see that you cannot get gain over a very large bandwidth. You will kind of run out when the basically the battery voltage will limit how far you can go here. Okay. So and that will be the bandwidth over which you can. So this is your gain spectrum of a semiconductor diode. So this is the gain spectrum. It's not a Lorentzian, it's not a Gaussian, it's determined by the band structure of the semiconductor or the density of states of the optical joint density of states is the gain spectrum of the semiconductor. And then we can do a low temperature, high temperature, and these have been measured to great detail, primarily because they have been used to make a lot of devices. And we'll see very soon, and you'll calculate it some by yourself, that these numbers can easily reach in the hundreds or sometimes even 1,000 inverse centimeter, but hundreds is more reasonable. Hundreds of inverse centimeter of gain instead of about 1 or so here, which, much higher generally. Okay, so and the game of the semiconductor laser would be, you have this sort of a gain spectrum over a small window over which you have gain, and then you build your cavity, you put some modes inside here, choose your FSR. If you want a single mode, put one here and have the rest out, but it will see that the gain bandwidth here, the width of the gain spectrum is very large compared to an atomic laser, very large. So if the center frequency is maybe 200 terahertz, this could be close to 1 terahertz. I mean, it's very large. So typically semiconductor lasers would be multimode unless you do some special tricks and all that on top of it. Typically it would be multimode, but one can obviously do some design and change it to single mode. Okay, so let me go back and first try to answer the question of the optical joint density of states, because again, I mean, all the other stuff we have kind of done before, but this is the new concept here. And this optical joint density of states is, let's see, what is a semiconductor? Really, it's a perfectly periodic arrangement of atoms. And we know that every atom has electrons tied to it. And what I'm going to plot here now is the energy allowed for an electron as it's going through, as it's meandering through this crystal now, right? So I think we know already that if you want to create a solid, there are some electrons that will be spent, or some electrons that will be used up in forming the chemical bonds that hold the crystal together, right? So I'm going to actually plot the energies. First of all, if you had just an arrangement of nuclei with positive charges like that, then if I release an electron, you right away know that the electric potential, it's kind of very strongly attractive when you get close, and then it so the total potential that an electron sees as it goes through a crystal would kind of roughly look something like that. So I'm saying the energy landscape that an electron would see as it moves through this periodic arrangement of atoms is going to look something like that. As it comes closer to, basically this is the repulsion between two positive charges here, but as the electron comes closer, it starts getting attracted. If it overshoots, but it sees a periodic potential. That's what it really sees as it goes through the crystal, right? There are some electrons that are closely bound. The orbital radii are very small, and they are core electrons. They don't even participate in the chemical bonding, some electrons, right? So they do not even participate in chemical bonding, and for them the orbitals are very closely bound, and they don't see, those electrons do not see the next atom at all. They don't experience any Coulomb interaction, none of that. As you know, this is an approximate statement because they always do, there's always a little bit, but what I mean is the lowest lying core electrons are completely, like 10 to the minus 30 or 40 times shielded, that you really, it's very close to zero, so it doesn't see it. And then there may be more electrons depending upon where in the periodic table you are, and these are really bound. They don't form what you call bands. The bands would be the outermost shell of electrons. Typically in semiconductors that we use for lasers, you have like 4s or 3s orbitals and 2s and 4s and 4p orbitals. So we combine. So as you go up in energy, there are these states that start interacting with each other much more strongly, meaning an electron state here that will kind of overlap very strongly with the next state here, and these are the ones that form bands now, and they also form the chemical bonds, right? So the same electrons that form the chemical bonds will form what we are going to call as the band structure of the semiconductor. And then if your electron energies are much higher than these potential minima, that will go through. These would be high energy electrons. If you shoot a 1 kilo electron volt electron through a semiconductor crystal and it's thin enough, you can go through without really getting captured anywhere. It's possible, right? But we are not going to look at that. We are going to look at low energy excitations. So the point I'm trying to make now is I'll have a bunch of electron states that will start forming bands. I'll have maybe another bunch here that will start forming another set of bands. And if I were to kind of clump them all together and say, how do all the energies look, in the energy scale, if I were to, forget about this details, but I just want to count how many energies are there in every bin of energy here. And you see that, for the lowest lying states, you have a huge number of states, but they're all the same energy. How many electron states? The number of atoms. Every atom is coming in with an electron or 3 electrons in a shell or whatever be it, right? So there's and then you go up a little bit, there are another set of electrons, but they're very sharp in energy. They have not interacted with other, the orbitals have not interacted with others, so these are very sharp in energy. And then you go up, and finally, when you go up to the topmost ones, you start getting interaction, and which is why what happens is these same number of electron states start interacting and seeing the potential of others. And another way to look at it is the electron wave starts spreading out. As it spreads out, it can kind of lower its energy compared to the mean. And so you start forming a band here. And then, so we are going to be most interested in semiconductors in the top 2 bands. So one, which is we'll call as the valence band, which is at 0 Kelvin, this is completely occupied. And at 0 Kelvin, the next band is conduction band, which is completely unoccupied. So there are 2 sets of, hopefully, at least qualitatively, you can make a connection of the origins here, where the electron states come from. These are just like atomic states, but these are slightly different because here the electron wave function, or rather the electron is kind of free to move through the crystal. It can kind of hop from one to the other. So it has formed a band, and it's free to move through the crystal, which is why there's a larger spread in its energy. And the conduction band is empty. The valence band is full under perfect equilibrium at 0 Kelvin. And the energy separation between these two is what we are going to call as the energy gap of the semiconductor, EG. Typically, of the order of, you can choose your semiconductors. So silicon is an indirect gap semiconductor, but it's 1 EV. Gallium arsenide, 1.5, 1.4 EV. And you can go all the way to 6 EV today with wide bandgap semiconductors like aluminum nitride and such. And so these are and we are going to ultimately look at a transition from here to here. So you can make lasers with all these frequencies now, all these energies now, using semiconductors by choosing different atoms, different materials. You can choose which one you want. You want a green laser, choose your 2.4 or 2.5 EV, choose which atoms will give you that, put those atoms into a crystal and make the laser. That's how the deal with semiconductors is. But we'll see a little later that even with the same material, by doing quantum wells or quantum dots, you can still tweak within the same material the energies of transition or the gaps of transition here. That's another one of the kind of most beneficial reasons or features of a semiconductor laser is with the same material. Like in an atomic laser, if you have neodymium, you have neodymium atoms, you are fixed with the transitions. You can't really mess with that. But in a semiconductor, by changing the size or the dimension of it, because these energies depend upon the size of the crystal, how far can the electron move freely, am I confined, am I mobile? Because of the energy, you can control it or you can engineer it. And therefore, you can engineer with the same material different wavelengths of emission. It's a very important property of semiconductor lasers. Okay, so now looking at it, looking at even a slightly bigger picture, so the conduction band edge, this is the smallest energy of conduction band, that's the highest energy of the valence band. And we're going to refer to the highest energy of the valence band as EV and the smallest energy of the conduction band as E sub C. These are unique energies. EC is the minimum of the conduction band and EV is the maximum of the valence band. I think those of you who have taken general chemistry sort of courses, this is the exact same thing as the highest occupied molecular orbital and the lowest unoccupied molecular orbital. Exactly the same thing, no difference really, right? Except these are not molecules. I mean, these are solids. They have extended states. In a molecule you have orbitals that are close. Electrons are not able to move too far, but here they are able to move through the whole crystal. So that's the difference here. Okay, so and just zooming out a little bit further in the whole range of things, the minimum of the conduction band here, I'm going to take that and just sketch it like this, EC and EV here, and this is your band gap that we defined, and you have a bunch of electron states here and a bunch of manifold almost of states here. And if I were to look at it, so I have a piece of semiconductor, let's say, and I put an electron inside it. Why does the electron stay inside the semiconductor? Why doesn't it escape into vacuum? That's because the lowest energy, the vacuum level is kind of out here, let's say E vacuum, meaning if you were to try to pull an electron out of a semiconductor, you would have to give it certain energy. So that is what's called the electron affinity of a semiconductor. Not very important, but just not very important for a laser, but it's may become important in the future. I'm just saying for this course it's all right. So electron affinity typically of the order of 4 electron volts. Or in other words, if an electron is sitting in the conduction band of a semiconductor, it is potential well. So all these variations here, and then you go out of the crystal into air. So it's kind of looking at inside the crystal, you have all these atoms, and because of the presence of atoms, the net energy of electron is slightly lower than if it was free, right? And if the electron was free, you are in the vacuum level, it would be moving in this energy, but because it's in the semiconductor, you have about 4 eV lowering of the energy inside the semiconductor. And that plus the band gap is typically called the electron affinity, because at 0 Kelvin, it's called the work function, because at 0 Kelvin all these states are occupied, and the work function of any material is how much energy do I need to give the material to kick an electron out from its highest occupied state into vacuum. So that's the electron affinity of a semiconductor. Right? So those are some of the details of this particular aspect of semiconductors here. But the band gap is kind of the more important quantity here. And just to locate ourselves, where in energy are we? We are about, in a conduction band minima, we are about 4 eV above the free electron, when the electron is not bound to the crystal at all. And if you're in the valence band, you are a further band gap below it. So further band gap below it. So for example, if you're in a very wide band gap semiconductor like 6 eV, so you are really almost 10 eV below the vacuum level. That electron is very hard to pull out, for example. And now, so what are these manifolds then? Why do the electrons kind of spread out like that? Why do they have a range of energies? Because now, unlike in an atom where the electron was bound to the atom, now because you have a crystal, the electron can move around. It has kinetic energy now. It can move around. So as a result, the total energy in a band, let's say in the conduction band, will be equal to what we're going to call as the potential energy. And when you are in an atomic system, you only had potential energy. There was no kinetic, because the electron was not mobile. It was tied to the atom. Right? But now it's in a semiconductor crystal, it can move around, and therefore it will have a certain kinetic energy, which is momentum squared by twice mass. That's what it's going to do. And that's what gives it its manifolds here. This thing we'll see is kinetic energy is what gives it the momentum. So the minimum of the conduction band is EC, which is, and here I'm going to write it as a function of momentum. So if you are in the conduction band, the total energy is the minimum of the conduction band, which is no momentum. Electron is not mobile, or it's very small momentum, is close to 0 momentum, and then plus this thing here, which is it's the same thing as, what is the total energy of a ball rolling down a hill? You've got to think exactly what do you mean by that question, because you can start by saying, well, the ball is made of mass, so yeah, it has mc square energy. We don't talk about that when we talk about the electron, a ball rolling down a hill with a certain velocity, because it has certain energy, it has gravitational energy with Earth, all that thing. You combine all that, that creates this potential profile for you. All that physics is kind of buried in there, right? All the other energies. So you're looking at an effective kinetic energy now, which is just half mv squared, for example, right? But we know that this is an excellent approximation to relativity and all that other things, gravitation. They're all things being considered. This is the kinetic energy in the end that helps you solve problems of, of classical mechanics. Exactly in the same way, a lot of relativistic quantum mechanics, etc., is buried inside this equation as well. Why do I have a conduction band edge? Well, because the electrons are in a crystal. It has standing waves. It has formed standing waves, etc. But all that stuff is going to give you this. And the fact that the electron is inside a crystal and not free to move like in vacuum. If the electron was moving here and you ask me what is kinetic energy, or what is p squared by 2m, what mass should I use? I'll use the mass of the electron. It's a free electron. Inside the semiconductor, it's not a free electron. And another triumphs of band structure theory or Bloch theorem is you can completely combine the presence of all these atoms and this periodic potential and say that, well, the electron is obviously going to accelerate, decelerate, and it has its own free electron mass me. But once I'm inside the crystal, it's going through a periodic potential. I can, this is let me just write this result down. It's called the effective mass theorem. And just a statement, obviously I'm not trying to derive it at all. All the details of the periodic potentials that the electron might see as it goes through a crystal can be completely absorbed by saying that instead of periodic potential, I'm going to have a fixed potential, but the mass has changed now. It's renormalized. Mass is different. And all the information of periodicity, what atoms there are, whether it's gallium arsenide, gallium nitride, indium arsenide, whichever semiconductor you take, is buried inside this mass of the electron, that information. So that whole sort of quantum and solid-state physics gets absorbed into this quantity, and you start kind of designing it like a classical system now. It says, well, I have potential energy, I have kinetic energy, but not the free electron mass. I'm going to use something called an effective mass now, m star. That's the difference here. And I'm not going to the details of that. If you have further questions, please come by. We'll discuss it during office hours, but not, yeah.
So EC, is that like, that's the potential, so is that like the energy of the lowest band?
Yeah.
I guess, is that supposed to be like the total energy of the
So it's the
conduction band?
The conduction band here is going to form a manifold of various energies, and if you are at the bottom of that manifold, the way you climb in that manifold to higher energies is using momentum. So you have kinetic energy as it moves, and this is the minimum.
Yeah, so that's the minimum. So the left is describing an energy within the conduction band. It's confusing because there's two ECs.
Right. Okay, so that's a good point. Let me put it this way: if you had no movement of electrons, if you had no kinetic energy, then you are at the bottom of the conduction band, and if you have any kinetic energy, you start rising in the manifold here, and you basically the larger the momentum, the farther you get from the band edge. This is the minimum of the conduction band energy manifold, the minimum. And the other very important thing, which is a pure result of quantum mechanics, is what is the momentum of the electron? So what's the momentum of the electron? We can say, well, it's mass times its velocity. But as you know, one of the big changes in last century of physics was all particles have wavelengths too. Right? So the momentum of any particle or any wave, according to the de Broglie relation in quantum mechanics, the momentum, no matter whether you have mass or no mass, is given by Planck's constant by the wavelength of that particle. No matter whether you're a photon, a phonon, electron, doesn't matter. The momentum of a particle is given by Planck's constant divided by the wavelength of that particle, which immediately enforces the fact that electrons must also have wavelength. And from here, I'm going to do a slight modification to it. I'm going to divide it and multiply it by 2 pi. Because h over 2 pi we have written as h bar. and 2 pi over lambda is what we have written as k. K is the wave vector of any particle now. Just like it was for photons earlier, now it's for electrons here. And so P is h bar k, and therefore the energy, instead of writing it in terms of momentum, I'm going to write it in terms of k. And the reason for that is because I'm going to relate this immediately to what wavelengths of light is it going to emit. And this wavelength lambda is going to relate directly to that now. So what wavelength of light? Is it green, blue, UV, infrared, is going to relate to this wavelength now. Right? So I write it in terms. So you can see this is what we did. We're out of time today. So we didn't reach the gain coefficient formula, but we'll start from here in the next class and say that I have a manifolds of states of electrons moving at different wavelengths, some at very long wavelengths, they are at low energy, some at high. I have similar manifold in valence band, and when there's a transition between the two, I'm going to emit a photon, right? And that's what's going to lead us to this, to the gain spectrum of a semiconductor, and we'll get the joint density of states using this relation now. Yeah. Right? So we're going to do that on Friday in class. So. All right, see you on Friday.